Okay, so the matrix equation A transpose AX equals A transpose B is known as what? The normal equation, or the normal equations, yeah. Good. If AX equals B is inconsistent, we search for an X hat, right? Instead of just an X, we search for an X hat that makes AX hat as close to B, right? You can't find an X that makes those things equal, so instead you look for an X that makes them as close together as possible. Okay. So that is, right, I'm just restating number 2 here. The distance from B to AX hat, that's those double lines mean the length from B to AX hat, has to be what compared to the distance from B to any other AX? Less than or equal to. Great. Okay, so today is the culmination of all the work we've done in chapter 6. Okay, so, and the whole semester, really, right? So much of this course dealt with solving the matrix equation AX equals B, right? But sometimes we saw that such a system would be inconsistent. Okay, there are no solutions. When a solution is demanded and none exists, the best we can do is find an X that makes A times X as close as possible to B, right? There is no X that can make that true, but we can make them as close as possible. So think of AX as an approximation to B, and the smaller the distance between B and AX, the better the approximation. So we call that distance B minus AX hat. It's called the least squares error of the approximation. The general least squares problem is to find an X that makes the distance from B to AX as small as possible. We call that value of X, X hat. So that's just stated another way there. So remember that no matter what X we choose, A times X is in the column space of A. Okay, so A times any vector gives you a vector in the column space of A. So this is exactly the picture that I drew for you last class, except that I had labeled this plane W, right? It was some subspace W. Now it's a very special subspace, the column space of the matrix A. So we want to find B hat or an AX hat, right? So here's B. You can't, it doesn't live in col A, right? So there is no solution to AX equals B. So we try to find the point in here as close as possible to B. AX hat as close as possible to B. That happens by dropping a perpendicular down to the plane. Okay, so the closest point to B in col A is we call B hat. It's the projection of B onto the subspace col A. And since B hat is the point in col A closest to B, just replace the equation AX equals B with AX equals B hat and solve that instead. And that will give you the X hat that makes AX and B as close as possible. However, finding B hat is a little tricky, okay? Because the technique that we learned last class for finding the projection of a vector into a subspace requires that you have an orthogonal basis to be able to do that. Okay, so we can always find a basis for col A. We learned how to do that like a little ways back, but it's not always orthogonal. Finding an orthogonal basis can be tricky, okay? If they happen to be orthogonal, you can use the method I just described. Find the orthogonal projection of B into col A using the formulas from last class, and then solve AX equals B hat instead of AX equals B. But if your basis is not orthogonal, a little bit of algebraic manipulation, shown in your text if you're curious, okay, reveals that you have this easier but equivalent equation, okay, you can solve. That A transpose AX equals A transpose B, and that matrix represents a system of equations called the normal equations. And the solution to the normal equations is the X hat that you're looking for. Okay. So these three things these four statements are all logically equivalent, which means they're either all true or all false. The last one being how to find X hat directly. Okay. All right, so let's do go ahead. Yeah.
I know it's
That's okay. Works all the time. Yep. Even if it's not orthogonal. Yeah. Even if it is orthogonal, it'll always work. A is m by n, so it's got m rows, n columns. So B should be in, this is x equals B, so this is m by n, so this has to be n by 1. So this is m by 1, no, it's m. Okay, so let's do an example. So before we can start here, we have to, we're going to show that this is inconsistent. It has no solution. Once we know it has no solution, we're going to search for the x hat, the best, the closest thing, right? The x that will make ax equals b as close to true as possible. So to solve the system, we just augment 2, 1, 1, augment with 0, 1, 2. You row reduce, and I have this all worked out somewhere. You get 1, 0, 0, 0, 1, 0, 0, 0, 1. So what is it that shows that this is inconsistent?
0 does not equal.
This last row here, it says 0x1 plus 0x2 equals 1. That's impossible. Okay, so that is an inconsistent system. It has no solutions. So rather than searching for a solution, I want to search for the least squares solution. Okay, I want to find the x hat that makes ax as close to b as possible. And I'm going to use the normal equations. Okay, so I'm just going to write down the normal equations here. Okay, so that says A transpose AX equals A transpose B. And then I'm just going to plug in all the stuff that I know. A is 1, 1, 1, 2, 1, 1. So the transpose just makes the rows columns and columns rows. So I have 1, 1, 1, and 2, 1, 1. Times A, which is 1, 1, 1, 2, 1, 1. Times X, which is just X1, X2, equals A transpose 1, 1, 1, 2, 1, 1, times B, which was given 0, 1, 2. So I just wrote it all out, plugging into the normal equations. The only one unknown now is x1, x2. That's the x hat. That's the thing I'm looking for. So I should be able to solve this. So I just do all the algebra out here. When I multiply A transpose times A, I get 3, 4, 4, 6. 3, 4, 4, 6 times x1, x2. And when I multiply A transpose times B, I get 3, 3. Okay, how do I solve that equation for x1, x2? Augment and row reduce. Yep. So just do 3, 4, 4, 6, augmented with 3, 3. And this becomes 1, 0, 0, 1, 3, negative 1, 1.5. So that's my x hat, 3, negative 1.5. What other equation I gave you? Oh, they're the same thing. Yep. If I were to solve this guy for x right at the beginning, you multiply both sides of the equation by the inverse of A transpose A. Yeah. I think it's just as easy to do this, but you can do it the other way if you want. Doesn't matter. Okay, so x hat comes out to 3, negative 1.5. So that is the closest thing to a solution that we can get. right? So if I go to my original equation, ax equals b, right? If I put in the x hat, that's as close to b as I can get. So let's just verify that. I want to find a times x hat. So a was 111,211 times my x hat, 3, negative 1.5, and get 0, 1.5, 1.5. That ax hat is also known as b hat, right? That is as close as you can get to b, but still being within the column space of a. So if I go back to my picture, right? B hat and ax hat are the same thing there. Okay. So this is also called b hat, otherwise known as the projection of b into col A, right? So we were finding b hats or x hats or y hats last class. We were doing it a different way, right? But we can get it this way now. Okay, so I would like to write b as the sum of a vector in col A and a vector orthogonal to col A. And then make sure we identify which is which. So b, I need to write as b hat plus z. This is the same thing we were doing last class. Right. B, I know it was given at the beginning. It's 0, 1, 2. B hat I just found 0, 1.5, 1.5. All right, then I have to figure out what to put in to make a z. I haven't figured out z yet. 0. What do I have to add to 0 to make 0? 0. What do I have to add to 1.5 to make 1? Negative 0.5. What do I have to add to 1.5 to make 2? 0.5. All right, which one of those vectors, 0, 1.5, 1.5, or 0, negative 0.5 is in col A? The first one, 0, 1.5, 1.5. This is in col A. Okay. Because it is just the product of A times x hat. A times any vector will give you something in col A. All right, and then this guy should be perpendicular to col A. So this should be in col A perp, right? In the vector space perpendicular to col A. But let's just verify that those two vectors are perpendicular, and then we'll know. So how did you verify two vectors are perpendicular? Dot product. So I'm going to do 0, 1.5, 1.5. Kind of look at it. 0, negative 0.5, 0.5. So you get 0 minus 0.75 plus 0.75, which is 0. So that vector, in fact, is perpendicular to col A. Okay, by definition, a least squares solution, that's x hat, is the vector that makes ax closest to b. So b minus ax hat, that distance should be less than or equal to b minus ax for any other x in Rn. So let's compute the length of b minus ax hat. Yes. Yep. Yep, so b minus ax hat is the length of z, yep, which is the length of 0, negative 0.5, 0.5, which comes out to the square root of 0 squared plus negative 0.5 squared plus 0.5 squared, which is 1 over root 2. Okay, so this is called the least squares error. Okay. approximately 0.707. You don't know why they're the same? 1 over root 2, right? Multiply the top and bottom of the fraction by root 2. You can do that, right? Because you can always multiply by a fancy form of 1. 1 times root 2 is root 2. What's root 2 times root 2? 2. That's why they're the same. Oh, square root of 1/2. When you take the square root of a fraction, you do the top and the bottom. The square root of 1 is 1. Square root of 2 is square root of 2. Okay. Sorry, I thought that you were asking about that. Okay. Okay, so now I want to pick any other x in Rn, anything other than x hat. Give me a vector. We're dealing in R2 here, so pick a vector in R2. 1, 2. Okay. Now I'd like to compute the distance from B to AX with the x that I just picked. That Rob just picked. Okay, so I need to calculate AX first. So that's 1, 1, 1, 2, 1, 1 times 1, 2. So this should come out as a 3 by 1. So 1, 2 times 1, 2 should be 1 plus 4 is 5. 1, 1 times 1, 2 should be 3, 3, 5, 3, 3. So now I need to take the length of B minus AX. B is 0, 1, 2. AX is 5, 3, 3. So I need the length of -5, -2, -1. That is 4 plus 1. Say it again. Root 30, which is approximately 5.477. Yeah, I think you could. Yeah, you could use a distance formula, take its derivative, set it equal to 0 to find the minimum distance. So that would be another way of finding B hat. Yeah. Yep. Yeah, anytime you hear that word, we're trying to minimize something. Calc 1 should pop into your head. Yeah. Okay, so let's verify. 1 over root 2 was 0.707, and B minus AX is 5.477. That is, in fact, smaller, right? So no matter what x we had picked here, it would come out so that 0.707 will always be smaller, because the x hat that we found makes B minus x hat as small as possible. All right, so this is the alternative method of finding a B hat, right? So we could have found B hat the way that we learned last class, right? You can find the projection of B into the column space of A if you have an orthogonal basis for col A, right? So to check that, I'm going to look at the columns of A and see if they're orthogonal. So 1, 1, 1 dotted with 2, 1, 1, and I get 4, which is not 0, so these are not orthogonal. Which means that using the methodology that we developed last class won't work in this case. We had to use the normal equations. But if we did have orthogonal columns of A, then you could proceed using the method we learned last class. And you can also use the method we just did. Yeah. So in this first problem for your activities, I'm going to have you at first do it the way we just developed, right? And then it turns out that these columns actually are orthogonal, so you can do it the other way also. Sorry. Yeah. I made a typo in the answers. and I fixed it. It's right here. Number 1, part F, part 3. In your packet, it says -1/2. It should be positive.